This video cast is on drawing Lewis electron dot structures and fits on dates 2, 3, and 4 of chapters 8 and 9. First, make sure that you have a periodic table of the elements in front of you. Make sure that you also have some blank pieces of paper in front of you, and you can write down some notes and follow along as we learn to draw Lewis electron dot structures. Lewis electron dot structures. Take the periodic table, put it in front of you, and let's review just a little bit about something called valence electrons. Valence electrons are electrons that are in the s and the p orbitals, s and the p orbitals of the highest energy level. And remember, the energy levels are the period numbers on the periodic table. This is energy level 1, 2, 3, 4, etc. Those are the principal quantum numbers. N equals, N equals, N equals. If you forgot what the principal quantum number is, remember it's represented by the letter N, and it tells you how far away from the nucleus those electrons are. And they are analogous to the periods on the periodic table. Okay, valence electrons are the s orbital electrons, and remember these two blocks are the s blocks, and the p orbital electrons, and remember these guys are the p blocks over here. Of course, helium is omitted from that because it only has two s electrons from the 1s orbital. This group right here, group 1, has one valence electron because it has the 1s orbital filled. This group has two valence electrons because it has the two s2 electrons in it, whether it be the 1s2, the 2s2, the 3s2, the 4s2, etc. Then we skip across this valley here where these metals are. Their valence electrons technically really are only these s electrons right here. And then we come over to this area where we get into a lot of nonmetals. This group, group 13, has 3 valence electrons. This group has 4. This group has 5. This group has 6. This group has 7. And this group has an octet, or 8 valence electrons. Except, of course, helium. Helium, remember, is an exception. It only has 2 valence electrons because it only has 2 electrons total. Same thing with hydrogen. It only has 1 electron, of course, and so it would never have p orbitals below it. Only 1 electron. So helium and a hydrogen really follow a rule of their own. They only want to look like the noble gas helium, which helium already does. And so they follow a rule called the duet rule and only want to have 2 electrons in their outer shell. Whereas everything else wants to look like neon, argon, krypton, or xenon and wants to get an octet of an electrons. But we'll talk about that in just a little bit. Let's go through the steps in drawing Lewis electron dot structures. First of all, why are Lewis electron dot structures valuable? Number one, because Lewis electron dot structures help us visualize how electrons are shared in molecular compounds. And remember, molecular compounds are where there are 2 or more nonmetals. Nonmetals only. Nonmetals only. These are covalently bonded compounds, and so they are shared electrons. Electrons that are shared. Okay? Electrons that are shared, and they're shared in the form of something called a bond. And we want to represent these bonds in a way so we can visualize these shared electrons and show how they stick together. There are 5 steps generally in drawing a Lewis electron dot structure. 5 steps generally in drawing a Lewis electron dot structure, and let's write down those 5 steps. And then there are, of course, a few exceptions. Step number 1 is to find the sum of the valence electrons. Sum of the valence electrons. Step number 2, once you've summed the valence electrons, then pick what's called a central atom. Pick a central atom. And the central atom is generally almost always the least electronegative atom. The least electronegative atom. If you forgot what electronegativity is, look once again on the periodic table. The most electronegative atom on the periodic table is fluorine right here, and the least is down here, way down here by cesium. So electronegativity decreases to the left and down. Decreases to the left and down. So the least electronegative atoms are down here, the most are up here. And since in Lewis electron dot structures we're dealing mostly with nonmetals, we'll mostly be talking about the electronegativity of these guys right around here. And of course the least electronegative ones would be the furthest away from fluorine if possible. Okay, so pick the central atom, usually the least electronegative. Then number 3, bond everything else around it. Bond everything else around it as possible. Bond everything else around it. Once you've done that, step number 4, fill, oh, I should go back here to number 2 because I forgot a point. The least electronegative atom, but it cannot be hydrogen. Cannot be hydrogen. And the reason it cannot be hydrogen is because hydrogen, remember, only has 1 electron. And hydrogen only wants to gain 1 more electron to be helium, and so it won't have lots of things bounded around it. Hydrogen is kind of in a class by itself. It'll only have 1 thing bounded around it ever. So that's why hydrogen can never be the central atom. Okay, bond everything else around it, and then what you want to do is you want to fill the octet. Octet, remember, means 8. Fill the octet of electrons. Fill the octet of electrons around all of those non-central atoms. And then lastly, fill the octet of the central atom. Now, there's some steps, and this is where it gets kind of tricky. Step number 5 and 6, etc. What happens if it doesn't work? What happens if it doesn't work? It doesn't come out. You've got extra electrons because you've been subtracting from some of these valence electrons. Well, then you've got to try double and triple bonds. Try double bond, try triple bond, and if those aren't working, then you have to do one of the weird exceptions that we'll talk about in a little while. So keep those 5 steps in mind. You've got them written down now. Put those off to the side and we'll refer to them as we do a whole bunch of examples. Let's do a bunch of examples following these rules. Do a bunch of examples following these rules, and let's start with something kind of simple. Let's start with PCl3. That's the first one we'll work with. First of all, sum the valence electrons. Remember, that's the first step. Have these rules in front of you. If you haven't written them down, go back in the video and write them down so you've got them, because they're not going to be on the screen all the time. Sum the valence electrons first. Okay, find phosphorus on the periodic table. Phosphorus is right here. Phosphorus is in group 15, so that means there's 5 valence electrons. Chlorine's in group 17. It means it has 7 valence electrons. So when I sum the total, phosphorus is 5, chlorine is 7 times 3. That's 21 plus 5. That gives me a total of 26 valence electrons. Step number 2, pick the central atom that's the least electronegative that's not hydrogen. Pick the central atom that's the least electronegative that's not hydrogen. Remember the rule, electronegativity decreases as you go to the left and as you go down. So my choices are chlorine and phosphorus. Well, phosphorus is way further left than chlorine, so phosphorus is going to be my central atom. So put phosphorus in the middle. Step 3, bind everything around it. Put the chlorines around it. I'm going to put dashes to indicate a bond, and remember, a dash indicates that there are 2 electrons being shared. 2 electrons being shared. This means 2, this is 2, this is 2. So take my total number of electrons, 26, subtract 2, 4, 6 from it. I'm down to 20 electrons. Keep a running tally as we go. Step number 4, fill the octet. Fill the octet of electrons and fill the octet of the central atom. Octet meaning 8 electrons around each because it wants to have a noble gas configuration. So 2, 4, 6, 8, 10, 12, 14, 16, 18. 18 electrons used to fill the octets of each one of the chlorine atoms, because remember there's 2 of them here in this bonded bond, 2 of them here in this bond, 2 of them here in this bond. Subtract 18 now from 20, because I had 20 electrons remaining. I've got 2 left over. Notice how dots we use. I put 2 on each side. That's just a general rule of thumb. You don't have to do that, but that's the general way that it's done. And these pairs of electrons right here are called unshared pairs because they're not shared with something else. These electrons right here that are written as a dash are called shared pairs because they're shared between the chlorine and the phosphorus. So I've got 2 electrons left over, and if I look, I've got octet, octet, octet of electrons right here. Phosphorus really only has 2, 4, 6 around it, so I need 2 more electrons in the central atom, and now phosphorus also has an octet. And I've now written my first Lewis electron dot structure following the 5 basic rules. Let's go on and let's look at something that's a little bit more difficult, something that's a little bit more tricky because it might not work out exactly like we wanted it to. Let's try an ion. In this case, let's try NO positive 1 charge. NO positive 1 charge. First thing to do, sum the valence electrons. Okay, valence electrons for nitrogen. If I look on the periodic table, nitrogen is in group 15, so it's got 5. Oxygen is group 16, so it's got 6. 5 plus 6. But what do I do if it's got a little positive charge? Well, if it's got a positive charge, that means subtract 1 electron. If it's got a negative charge, that means add an electron. And of course, it's got a positive 2, subtract 2. If it's got a negative 2, then subtract, or add 2 to it. So I subtract 1 here, it has a total of 10 valence electrons. So we've got 5 electrons from nitrogen, 6 from oxygen. Subtract 1 because it's a positive 1 charge here, so we've got 10 valence electrons to work with. Here we don't really have to worry about a central atom because there's just nitrogen and oxygen. So bond them. All right. That takes care of 2 electrons. 10 minus 2 is 8. 8 electrons remaining. I can go 2, 4, 6, 8. And I pause because now I look and I see that I've obtained an octet. 2, 4, 6, 8 electrons around oxygen, but I have not obtained an octet around nitrogen, and so I'm not fulfilling the goal of obtaining 8 electrons around everything. So if it doesn't work, well, general rule of thumb, if it's not working and I'm not filling an octet, I've got to go to either double bond or triple bond. Well, let's try that. Okay, so let's start here over again. N double bond O. This takes up 2, 4 electrons. Remember, I started with 10. Take away 4, I've got 6 remaining. 2, 4, 6, 8. Oh, 2, 4, 6, 8 electrons around oxygen. 2, 4, 6, 8, 8 electrons around nitrogen. Hey, it looks like it's going to work. Now for ions, put them in brackets and put the little charge up above them too. And that indicates that this is a possible Lewis dot structure for NO positive 1 charge. NO positive 1 charge. And I ran into some trouble originally, gave up, started again, this time with a double bond. Sometimes double and triple bonds are necessary to complete the octet and make sure that I've got 8 electrons around everything. Let's go on, let's try some other exception strange guys. Or maybe they're not exception strange guys, but they're just some other rules that might be a little bit more difficult. Let's try this ion, NCO negative 1. This is known as the cyanate ion. The cyanate ion contains nitrogen, carbon, and oxygen. Let's say I want to draw the Lewis dot structure of it. Look on the periodic table to find out how many valence electrons N has, C has, and O has. So looking on here, carbon has 4 valence electrons, nitrogen 5, oxygen 6. So 4 plus 5 plus 6, hey, that gives me 15. Notice it also has a negative 1 charge, which means I need to add 1 electron to it. The reason it has a negative 1 charge is because it has an extra electron. So there's a total of 16 valence electrons to use. Let's go ahead and pick a central atom, the least electronegative. And if I look on the periodic table, oxygen, nitrogen, carbon. Ooh, carbon's the furthest to the left because remember, electronegativity decreases to the left and down. And so if they're all just straight to the left, carbon's going to be my least electronegative. So let's put carbon in the middle, bond an oxygen to it, bond a nitrogen to it. I've used up 2, 4, 4 electrons. 16 minus 4 is 12. 12 electrons remaining. If I go 2, 4, 6, 8, 10, 12, I've done wonders for oxygen, for nitrogen, but carbon's left all by itself with only 4 electrons around it. It'll never do that. It'll never do that. Carbon won't have an exception where there's only 4 electrons. So what do? Well, I got to go to double or triple bonds, right? Got to go to double or triple bonds. So let's give it a try. How about I try this? Nitrogen, double bond, carbon, double bond, oxygen. Let's just try it and we'll see. And some people don't like Lewis dot structures because sometimes you have trial and error and it doesn't work, but you got to get over that. 16 minus 2, 4, 6, 8 leaves me 8 electrons to go. 2, 4, 6, 8. Hey, it's a possible Lewis dot structure, right? Because I've got 8 here, 8 around the carbon, 8 around the nitrogen, put brackets around it, give it a -1 charge. That's a possible Lewis dot structure for thiocyanate. But what happens if I wanted to draw this NCO another way? And maybe some of you already thought of this. Maybe you didn't, but let's just pretend you did. NCO. maybe I put a triple bond O right here. Oh, okay. 2, 4, 6, 8. 16 minus 8 leaves me 8 electrons. Okay, 2, 4, 6, 8. Hey, look, I've done it again. 2, 4, 6, 8 around nitrogen. 2, 4, 6, 8 around carbon. 2, 4, 6, 8 around oxygen. Put brackets around it. Put a negative sign there. Hey, it's another possible way to draw it. Now you're probably jumping it down and saying, oh, well, but which one's right? Well, let me throw this at you. How about I happen to do it this way? Negative 1 charge. 2, 4, 6, 8, 10, 12, 14, 16. 16 electrons still used. This time the triple bond's over here between the carbon and the nitrogen, and the single bond is between the carbon and the oxygen. Now, which one's right? 3 different possible ways to draw it. Are all of them right? Well, sort of, but sort of not. There is a way to determine which one is the most probable or possible, and perhaps the better of the 3 structures. And the way to do that is to assign what's called formal charge. To assign formal charge, there's a small little mathematical thing that you do for each atom, small little mathematical thing you do for each atom in the ion or in the Lewis electron dot structure. And then the rule is you want to get as many zeros or as close to 0 as you can for each one. As close to 0 as you can for each one. So here's the math formula. Math formula is periodic table electrons that are assigned to that atom minus the electrons that are assigned to it or given to it in the Lewis dot structure, minus the ones in the Lewis dot structure. And then whatever number you get here is called a formal charge on that particular atom in that ion. So let's go through and do a couple of them. Let's take this nitrogen, for example. Notice the number of electrons assigned to it on the periodic table for nitrogen is 5. Okay, 5. And then I subtract from it the number of electrons assigned to it in the Lewis dot structure. The only exception is if it's a bond, if it's a bonded pair, only count it as 1, because you're technically splitting it up and saying nitrogen has 1 and carbon has 1. So this has got 1, 2, 3, 4, 5, 6, 7. 5 minus 7 is negative 2. So a negative 2 formal charge on this nitrogen. For carbon, if you look on the periodic table, there are 4 electrons assigned to carbon, because it's in group 14. And in this Lewis electron dot structure, there are 1, 2, 3, 4. 4 minus 4 is 0. So I have a formal charge of 0 assigned to that carbon. Hey, didn't I say you want to have as many zeros as possible in the Lewis dot structure? You're right. That's exactly what you want to do. Now let's take a look at this oxygen. If you look on the periodic table, this oxygen right here has got 6 valence electrons. Oxygen, 6 valence electrons. And then in the Lewis electron dot structure, 1, 2, 3, 4, 5. 6 minus 5 is 1. So there's 1 valence electron on this guy. So in this structure, excuse me, I have formal charges of negative 2, 0, and positive 1 for this structure. Okay? Now let's assign them in another structure. Let's take, for example, this one, the first one that I drew right here. Nitrogen, 5 on the periodic table, minus 1, 2, 3, 4, 5, 6. 5 minus 6 is negative 1 for this nitrogen. Carbon, 4 minus 4, 0, because there are 4 assigned here, 4 on the periodic table, so it'd be 0. This oxygen, 6 assigned on the periodic table, 1, 2, 3, 4, 5, 6. 6 minus 6 is 0, so this oxygen would have 0. So for this structure, I have negative 1, 0, and 0. Hey, that's getting better. At least more of them are zeros, right? It's probably more possible to have this structure than this one, because this one has 2 zeros and a negative 1. Let's look at this last one. Nitrogen on the periodic table is 5. Assigned in the structure is 1, 2, 3, 4, 5. 5 minus 5 is 0. Carbon, 4 assigned to it on the periodic table. 1, 2, 3, 4 assigned to it in the Lewis dot structure, so 0. Ooh, 2 zeros so far. Oxygen right here, 6 assigned to it on the periodic table. 1, 2, 3, 4, 5, 6, 7 assigned to it on this Lewis dot structure, so negative 1. So for this one, I'd end up with 0, 0, and negative 1. Which one is the best? The negative 2, 0, or 1, the negative 1, 0, and 0, or the 0, 0, and the negative 1. And you're probably just struggling between these two because you're saying, hey, this one's only got one non-zero charge. This one's got only one non-zero charge. Well, here's the rule. Here's the last rule. Get the one that has the most zeros. That's first. Then, if you have to have a negative number, like you have a negative number here on nitrogen and negative number here on oxygen, choose the one that has the negative charge on the most electronegative element. On the most electronegative element. So you got to look between nitrogen and oxygen. Who's more electronegative? Well, let's look at the periodic table and see where they are. Here's nitrogen right here. Here's oxygen right here. And remember, electronegativity decreases to the left and decreases down. Well, nitrogen is a little bit less electronegative than oxygen. Oxygen's a little bit more. So probably the best one then would put the negative charge on the oxygen. So this structure right here would be the most possible or the most probable, simply because after I assigned formal charges, I got the most zeros, and I put the negative charge on the most electronegative elements. All right, let's take a look at a few exceptions now. A few exceptions. So far, we've looked at Lewis dot structures. So far, we've looked at Lewis dot structures that have had some double bonds, and we've also looked at some that have some triple bonds. And in a little bit, we'll look at ones that have some strange bonds as well. But let's go back to the double and triples, the ones we had right here, and ask, well, I know that this is the most probable at Lewis electron dot structure here too, but what about these other two? Well, there might be a little bit of those, and they're possible, but this one is the most probable at all. Let's look at one other function of double and triple bonds. One other thing of double and triple bonds. And let's take a look at some consequences of double and triple bond things as well. Let's look at NO3 minus 1, the nitrate ion. Let's draw the Lewis electron dot structure of that. Nitrogen has 5, oxygen has 6 on the periodic table. There's 3 oxygens, and add 1 more because it has a negative 1 charge. So 18 plus 1 is 19 plus 5 is 24. 24 valence electrons. Put the nitrogen in the middle because it's the least electronegative. Now bond the oxygens around it. Turns out it's not going to work very well because I only have, I'll have an unshared pair on the nitrogen there, and I won't have enough to fulfill the octet. So let's go with the double bond. Double bond right there, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Put brackets around it, and lo and behold, there's my nitrate ion. That's one way to draw it. What about another way? Could I draw it like this? I'll just omit the extra electrons. I should have 6 around here, 6 around here, 4 around there. Now the double bond's not here, but here. What about this one? Would that be okay as well? Now, if I go through and I assign formal charges, I'm going to find out that it doesn't make any difference because every one of them is going to have an oxygen with a 0 and some oxygens that have a negative 1. And my nitrogen is going to end up with a positive 1, no matter what I do. They're all going to be the same. So which structure is it really? Well, this brings up an interesting double-triple bond complex. This and this and this, all three of these structures actually are correct. And actually, if you go in and you measure the strength and length of each one of these bonds right here, you find out that this one is not a double, this one's not a single, and not a single. You find out that each one of these bonding areas is actually like 1 1/3 bonds. 1 1/3, 1 1/3. Because really what this structure does is it switches between each one of these structures. The special name for this swapping between structures is resonance. Resonance. We say that nitrate resonates between 3 different structures and that the double bond actually swaps from place to place to place. And it swaps so quickly, we'll look a little bit more in Chapter 9 on how that actually happens, that when you go in to measure it, you don't see the double bond at one spot at one time, or a single bond at one spot at one time. You see actually the strength and length of like a bond and a third at one time. This resonance occurs because the double bond is shared throughout the molecule, making it a little bit more stable and a little bit stronger. Those are called resonance structures, and you actually draw all three, and you actually draw arrows between them to indicate that those are resonating structures. Lastly, in this video cast, let's look at three exceptions. Three exceptions to drawing Lewis dot structures. Number one, let's look at where there's an odd number of electrons. Number two, let's look at where there are less than an octet of electrons. And then number three, let's look at where there are expanded octets, or more than 8, greater than 8 electrons somewhere. Odd numbers of electrons, less electrons, and expanded octets. Write those down. We're going to look at each one individually and do an exceptional example of each one. First of all, let's look at an odd number of electrons. Odd number of electrons are really weird. They're usually on substances that don't hang around very long. And an example is the gas NO, nitrogen monoxide. Okay, nitrogen has 5 valence electrons, oxygen has 6, we have a total of 11, an odd number of electrons. Well, what do? Well, I draw nitrogen to oxygen, that gives up 6 electrons right there. Hey, that leaves me with 5 left, 2, 4, 6, oh no, that doesn't work at all. Let's try again. How about, whoops, I drew too many oxygens there to start with. Let's try that again. NO, 1 bond. 11 total electrons minus 2, that leaves me with 9. Should I try a double bond? I'm not sure. How about this? 2, 4, 6, 8, 9. That might work. That leaves me with 2, 4, 5 on nitrogen. How about a double bond? 2, 4, 8, 9. That still leaves me with an odd number of electrons on nitrogen. And you're stifled because you're like, well, which one really works? And as a matter of fact, 2, 4, 6, 8, 10, 11 electrons right here probably works the best, because we end up with an odd number of electrons on nitrogen, which makes the compound very unstable, and yet you're still using up all the electrons. Odd ones are very rare. You don't see them very much, but now you've seen one. Let's move on from those, because it's not worth spending a lot of time on those because you don't see them very much. Let's look at less than an octet. Less than an octet. Let's look at this molecule example, BF3. Boron, 3 valence electrons. If I look on the periodic table, boron is located right here, 3. And then fluorine. Fluorine is located in group 17, so it has 7 valence electrons. 3 plus 7 times 3, so 21 plus 3 is 24. 24 valence electrons. Let's put boron in the middle. Bond the fluorines around it. Boron, of course, is way less electronegative than fluorine, since fluorine is the most electronegative. This uses up 2, 4, 6 electrons. 24 minus 6 leaves me with 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. Hey, there it is. 18 electrons. Boron trifluoride. Boron has less than an octet of electrons. And it turns out that's the way boron acts. That's the way boron acts. It can have less than an octet of electrons. We'll look at it a little closer in chapter 9 as to why boron does that, because it has to do where the electrons are in the S and P orbitals. Lastly, let's look at the one exception that does happen quite often. Odd doesn't happen very much. Less happens once in a while. But expanded octets, or more than 8 electrons, happens more than you realize. Happens more than you realize. If an element is in the third period or below, and let's look on the periodic table so you know where I'm talking. Third period or below, that would be right here, aluminum, silicon, phosphorus, sulfur, chlorine. Here, any of these or below, it can have what's called an expanded octet. It can have 8 or more than 8 electrons in its outer shell. And the reason it can do that is because these, and anything below, have d orbitals. And the d orbitals, in this case right here for these guys, are unfilled. These d orbitals might be partially filled, or it has d orbitals that are unfilled that are above the energy level where there are electrons in it. You might say, yeah, well, sulfur doesn't have any d electrons. The highest it has is 3p4. You're right, but the 3d orbitals do exist. They're just not filled with electrons right now. So let's take a look at a couple of exceptions to this rule. PCl5 is one of them. Phosphorus, 5 valence electrons. Chlorine, 7 times 5 is 35, plus 5 gives me a total of 40. To bond 5 things around the phosphorus, you are now going to have 5 chlorines going around it. Yep, that's what it looks like. And this takes up 2, 4, 6, 8, 10 electrons, now down to 30 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30 more electrons done. There it is, PCl5 with 2, 4, 6, 8, 10 valence electrons around it. It has an expanded octet. Can phosphorus have an expanded octet? Yes, because phosphorus is in the 3rd period or below. 3rd period or below things can have that. Let's take a look at another example. If these substances exist, ones that contain noble gases, in this case XeF2, they almost always have an expanded octet, because of course xenon is a noble gas. It doesn't really readily form substances, but when it does, it can have an expanded octet because it's got those extra d orbitals that aren't filled. Xe, 8 electrons. Fluorine, 7 times 2 is 14, plus 8 gives me 16 or 22. Let's see, 14 plus 8 is 22 electrons. Put the least electronegative atom in the middle, xenon, bonded to the fluorines. Okay, that takes up 4 electrons, so 22 minus 4 leaves me with 18 electrons left. So let's go 2, 4, 6, 8, 10, 12. 18 minus 12 leaves me with 6 electrons left. So let's go 2, 4, put the extra electrons in the central atom, and there's my XeF2, and that is a possible expanded octet that I could have, because xenon has those extra d orbitals that I could fill up. One last example of an expanded octet, and then we are done. Let's try ICl4 minus 1, an ion. ICl4 minus 1, an ion. Iodine, of course, has 7. Chlorine has 7. Times 4 is 28. Plus 1 more, because it has a negative 1 charge. So 29 plus 29 plus 7 is 26. I'm sorry, 36. So 36 electrons. 28, 29. 29 plus 7 is 36 valence electrons. Now put the iodine in the middle. Put the iodine in the middle because it's the least electronegative. Bond the chlorines around it. 1, 2, 3, 4. Okay. It uses up 2, 4, 6, 8 electrons. 36 minus 8 leaves me with 28 electrons. Go ahead and fill the octets of the chlorines. 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. So 1, 2, 3, 4 times 6 is 24. 28 minus 24 is 4 electron pairs, or 4 electrons left. 2 pairs left. Put them on the central atom. There is my ICl4. It's an ion, so put brackets and a negative 1 charge up there. There's my ICl4 expanded octet iodine right here. Generally, expanded octets can never go more than 2, 4, 6, 8, 10, 12 electrons around it. You can either have 10 or 12 in an expanded octet. You'll never see any more. That's pretty much a never. But you will see some expanded octets. So, summarizing, Lewis electron dot structures, ladies and gentlemen, help you visualize electrons shared. It only happens in nonmetals. Remember, it only happens in molecular covalently bonded things, and electrons are shared. Sum of the valences, pick the central atom that's the least electronegative, can't be hydrogen, bond around it, fill the octet of the central. If it doesn't work, try double or triple. And we talked about 3 exceptions: less than an octet, odd number of electrons, and of course expanded octet guys like this. Good luck with your Lewis electron dot structures.